That is the Milky Way. We have massive black hole at its center. And so that's why we are very fortunate, we are eager to know what is called black hole. And we are very funding about the mystery of the black hole. The question arises in our mind: how do black holes form? How big black holes are? If black holes are black, how do scientists know they are there? Could a black hole destroy Earth? We know that space satellite, the space telescope, the black holes and other elements in the galaxies. And how is measurement taken out? One important one is arises in our mind. How do the stars that are very near to the black holes act differently than other stars? And we are very fortunate. We have such astrophysics with us, who is very much specialized in the area of phenomenology of active galaxy driven by supermassive black holes using multi-wavelength observation ranging from radio to X-ray wavelengths. So Professor Prajval Shastri ma'am with us, and I think she is the right person who is alumnus of IIT Mumbai TFR, and he has extensive doing work. He has investigated physics of accreting central supermassive black hole in distant galaxy. So she's the right person who will explore the world in front of us, and we know many hidden things behind the black hole. So once again, I express my heartfelt thankful and gratitude to the ma'am. You are being with us in spite of busy schedule. You are giving me time for physics department. Thank you very much. Once again, I welcome everyone to this virtual platform in a beautiful evening. Have a good day, and wish the webinar will be a successful one. Thank you very much.
Thank you, sir. May I now request the coordinator, IQAC, Dr. Joyanta Hendricks, to address the gathering.
Good morning, everyone. I, on behalf of IQAC Digboi College, welcome Professor Prajval Shastri, even in Astrophysics, Indian Institute of Astrophysics, Bangalore, and all the participants to our Digboi College. Actually, we had proposed to hold a series of webinars during the lockdown period for the students as well as the faculties of the different departments. Today, Department of Physics has organized this webinar, and Professor Shastri delivered a talk on hunt for the black hole. I think it is fruitful to all of us, and I wish all the success of the seminar. Thank you.
Thank you, sir. May I now request Dr. Deep Puri, Faculty Department of Physics of Digboi College, to give a brief introduction of our resource person.
Thank you, madam, for giving me this opportunity to introduce our dear speaker, Professor Prajval Shastri, madam. Professor Prajval Shastri has been an eminent astrophysicist for over 35 years. She has been retired as a faculty from Indian Institute of Astrophysics, Bangalore in the year 2018, and is now a senior associate in the International Center for Practical Science Institute of Research, Bangalore. She did her master's in physics from Indian Institute of Technology, Bombay, and completed her PhD from Tata Institute of Fundamental Research, Mumbai. She has held several post-PhD positions in prestigious institutes throughout the world. Some of them are as a postdoctoral fellow in University of Texas, Austin, USA, and University of California, Berkeley, USA, as a visiting scientist in Harvard Smithsonian Center for Astrophysics, USA, as a Fulbright Fellow in Stanford University, USA, as a distinguished visitor in Australian National University, Australia. A research specialty lies in the physics of active galaxies using radio, optical, ultraviolet, X-ray, and gamma ray observations. She has more than 50 research publications, international peer-reviewed journals, and has supervised a number of PhD students. Dear ma'am, we are grateful to you for taking out some time for us from your busy schedule. Looking forward to your lecture, ma'am.
Hello, can you hear me? Hello, can you hear me?
Ma'am, your voice is not audible.
There is some disturbance in the connection.
It's clear, ma'am.
Is it
clear, ma'am. Okay.
is it okay now?
It's okay.
Okay. So I will share my screen. Should I start? Because I didn't hear what Rashmi had to say. Am I ready to start?
Yes, ma'am.
Okay. So good morning, namaste, everyone. It is a real pleasure, I have to say, to give this talk. When Rashmi emailed me, I was very happy that this time was free, and I could immediately say yes to her. I have only rarely visited your part of the country. I've been to Guwahati once, and then I've visited Shillong, and I've been to Arunachal Pradesh, also to the Eagle Nest Sanctuary, and so on. It was a beautiful. Both of those trips were very, very beautiful, and so at least I'm happy that I'm able to remotely connect with you and share a little bit about what excites me in my work. So I will start to share my screen, and if you can confirm. So can you see my screen?
Yes, ma'am.
Okay.
Yes, we can see the screen. Yes, ma'am.
Okay, good. Okay, so I will talk about the hunt for black holes, and Dr. Saiki has already introduced the topic very well. What you're seeing here is a picture of the Milky Way. Cannot do this interactively. I did. I would my talk interact, but I hope have interaction at the end of the talk. But now I have to just one way. So you probably realize that this is the Milky Way. And this photograph was taken by a friend of mine who's a very good astrophotographer. His name is Ajay Talwar, and he goes to the best places in the country to take photographs of the sky. The reason he has to go into all this trouble is maybe obvious to all of you, because you live in an area which is not so light polluted as the area where I live. I live in Bengaluru, and the light pollution is really, really bad. When I was a child, I was born in the year after Sputnik was launched. And it was a very exciting time for science. Everybody talked about this major achievement of humanity having created an artificial craft and launched it into space. And more importantly, as a child, we used to lie in our garden on a mat after dinner and watch the sky. And we could see the Milky Way. We could see lots of stars, of course, and planets. We could even see artificial satellites which would make their way through the stars. It was very beautiful, but that is something that the next generation does not have access to. And the reason is this. So maybe many of you have seen this picture. It's the picture of the Earth taken at night from outer space. And you can see that this is all the lighting that has been used on Earth. And you might think that on the face of it, it looks like a pretty picture, right? But if you think about it, we realize that all this light that is seen in this picture is actually wasted light, because it is going away into sky. The lighting that we do is meant to light our lives. It's meant to light our ground and, to show us where to go and to study and all of that. But we don't design our lighting to be directed towards the Earth. We also do too much lighting. We don't need all that lighting. And as a result, we are spoiling our skies. And so when I talk to audiences like yours in my part of the country, and I ask them, how many of you have seen the Milky Way? There won't be a single hand up. Sometimes there'll be one hand up, and then they will say, I saw it on TV. So, this is the unfortunate state of affairs. So I would like to urge you, I know Digboi is a more developed part of the country. I looked at, the picture I showed you, you can access it yourself on the internet, and you can zoom in just like on Google Maps, and you can see in your area, what is the extent of light pollution. And so it would be a very worthwhile effort if you formed a movement to have the lighting in your areas, more, to first of all have it less, and to have it designed so that it points at the Earth, so that your skies, which will be definitely better than our skies here in Bengaluru, will be less polluted. And so this is a thing about astrophysics that I will talk to you about what interests me and the field of my research. But what I want to convey is that astrophysics is really for everyone. So it's not like I'm doing this because I want all of you to become astrophysicists, right? I mean, we don't want everybody to become an astrophysicist, because then, who will make movies and who will, play football and so on. But we want astrophysics to be exciting for everyone. So everyone should be able to understand at least the basics of what drives the different phenomena in the sky. And so when there are surprising phenomena, when there is a comet, which is there now, I hope some of you will be able to see it. When there is a comet or an eclipse or a meteor shower, everybody should be able to enjoy them, and not just enjoy the visual beauty, but also understand what is the physics behind those phenomena. Yeah. So with that bit, let me move on to the topic of my talk. So Dr. Saikia already said that black holes are chunks of space-time from which even light cannot escape. Yeah, so the name black hole tells us what that is. Now, to explain that a little bit more, I said light cannot escape, right? So all of you remember this calculation of escape velocity that you did in high school. And you know that the escape velocity depends on the mass of the object that you're escaping from. Right, so for example, from the Earth, the escape velocity is about 11 kilometers if you are at the surface of the Earth. And so this, you can calculate this quite easily. I'm sure all of you know the formula for this. And so there is a relationship between the mass and the distance from that mass and the speed. And this relationship gives you what is the escape velocity. Now, obviously, when you have a larger mass, the escape velocity is higher. So many people, even as early as in the, a couple of 100 years ago, they thought about this and they imagined, what if the object is so heavy that even light cannot escape? So light has a speed of about 300,000 kilometers a second. And so what would it take to make a mass that would be so heavy that the escape velocity would be equal to the velocity of light? If you imagine an object, then obviously even light cannot escape from that object, right? Now, it turns out that they got this, so in that formula, you set the escape velocity to be c, that is, to be the velocity of light. If you do that, you get a relationship between r, which is the distance from the center of the mass, and m, which is the mass itself. So in other words, if you can squeeze a mass, say m, into a size which is given by this formula here, then that will be an object from which even light cannot escape. Nothing can escape, including light. So that becomes a black hole. Now, this was done, as I said, way back. There is some documented evidence, for example, that somebody called John Mitchell imagined this and did this calculation and got a formula. Now, this formula, and this idea is sort of intuitive. You can imagine, because we all are familiar with escape velocity. We all know that if we jump away from the Earth, we are going to fall back. And if we should not fall back, then we have to be launched with a very high speed. All this is very intuitive. It turns out, though, that when you talk about this kind of a mass from which even light cannot escape, that is, when you talk of a black hole, there are consequences that are not intuitive. These consequences can only be explained by the general theory of relativity. So this formula that I just talked about, where you have a relationship between the mass, the radius, and the velocity, that is from classical physics, from Newtonian physics, right? We all learned that. And we just did this game of replacing the velocity with the velocity of light, and we got a formula. But that classical physics and that formula does not explain all the other non-intuitive consequences of black holes. Okay, so for example, what these pink grids are showing, on top you have a two-dimensional grid which is represented by these coordinate axes. If you put a mass at the center of that grid, then what actually happens in reality is that the space itself curves because of this mass. Now, this cannot be explained by Newtonian physics. And it was Einstein, with his general theory of relativity, who first predicted that this is what will happen to space-time, as we call it, if you have a mass there. Okay, so if you have empty space, then it will look like the grid on the top. But if you put a mass there, anywhere, then the space-time will curve. So what is space-time? That's just a fancy way of saying that, we have to look at space and time together. So for example, if I say I'm here in Bengaluru, that is not a complete description, right? Because I have to say I'm in Bengaluru now, because in 2017, I was in Guwahati in October for 2 days. So I have to say if I want a complete description, I have to say where I am and when I am, right? So that is what is space-time. You can understand it like that. Because I'm not going to, you know, like explain to you what is the general theory of relativity. I wouldn't even be able to do it. But keep in mind that this is what is space-time. Now, here that space-time is represented by this coordinate grid on top. And if you put a mass there, it will curve. This is what Einstein's theory of relativity says. And this is not something that Newtonian physics says. So now this is true regardless of the mass. So, you know, me being where I am curving the space-time. My laptop is curving the space-time. Each of you is curving the space-time. But our masses are so small that that curvature is simply not measurable. We just don't notice it. And that is why, you know, Newtonian physics didn't try to explain it, because this is not something we would notice on a day-to-day basis, because the effect is very, 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 very small. However, a black hole, as we know, is very massive. I mean, even the Earth does curve space-time. So that it took a long time to notice that. It is not something that came about. In fact, it is very interesting that the GPS system, which we have on all our cell phones, it is when the GPS system was invented, that is when people realized that the curvature of the Earth is quite, the curvature of space-time because of the Earth is quite significant. And if GPS has to work properly, they have to take that into account. So they have to use general theory of relativity to make GPS work. So this is something really interesting. Anyway, so as I said, the Newtonian physics gives you the correct formula for the relationship between the size and the mass in order for something to become a black hole. But it does not explain the curvature of space and so on. So now the only thing I want you to remember from now on is that this very simple idea, which John Wheeler put forth many years ago, that mass tells space how to curve. Soon after Einstein proposed his theory of general relativity, 1 year later, a scientist called Carl Schwarzschild found a solution to the Einstein equations. And that formula, it turned out, is exactly the same formula that comes out of Newtonian physics when we equate the escape velocity to the velocity of light. I just want to point you out to some very simple desktop experiments which are there on the internet, which demonstrate how masses curve space-time. This is not exactly curvature of space-time, because you're representing space-time by something, like in this case, some sort of rubber sheet or something, but it at least gives you the idea of the distortion that masses make on the space-time. So now to take this formula, which tells you what is the size if a certain mass has to be a black hole, the question is there a minimum mass? So do black holes have a minimum mass? And this formula directly doesn't tell us, right, whether there is a minimum mass or not. So are there electron-sized black holes, right? And are there black holes seen in the laboratory? The answer is, so far, no black hole has been seen in a laboratory. Okay, and there have been speculations about very tiny black holes, electron-sized black holes, and so on. And there's a whole Wikipedia page on that, on micro black holes, which you can read. I won't go into it. There is no empirical evidence for such things, so we don't know that they exist, but they're still in the speculation regime. Okay, so the only black holes we really know are in the cosmos. And as Dr. Haikia already said, we know that stars can collapse into black holes. So scientists called Oppenheimer and Volkov proposed a long time ago in 1939 itself, that when stars go through their evolution, eventually, if they're heavy enough, they will collapse into black holes. So all stars don't collapse into black holes. The stars which are relatively light will collapse into something called white dwarfs, which maybe you've learned in your books about. Slightly heavier stars will collapse into magnetized compact stars called neutron stars, which is again a huge story in itself. But very heavy stars will collapse into something, if that remnant that they collapse into is heavier than about three times the mass of our sun, then we think that they will become black holes. So have we seen them? How can we see them? Clearly, it's not easy to see black holes because they are black, right? So it's a difficult process. Now, to go back to this idea of masses curving space-time, this is just a representation to show you how the Earth would curve space-time. And what this diagram at the bottom left is showing you is they have drawn some grid lines on the background sky where you see the stars and so on. So those orange grid lines are just artificial, just to explain to us what's happening. And what it is showing is that the light is curving, as you can see. So this is what a mass curving space-time does. This is what curving of space-time means. It means that light, which we expect to travel in straight lines, if the space-time is curved, it will no longer travel in straight lines. It will travel along the curvature. So you will see a curvature in the path of the light. And so therefore, ideally, if we are hunting for black holes, this is the way to hunt for them. So this is here, I'm showing you a piece of the Milky Way, just a piece of the sky, which I showed you earlier. Suppose you imagine that there is a black hole in there somewhere. What will happen is the black hole itself, we can't see. So it'll show up as a black, it'll look black. But all the stars around it, right? The light from those stars will not come to us in straight lines. They will come to us in curved lines. And so you will see the whole sky all distorted. That is what is shown here. But this is not a real picture. Okay, this is just imagining what will happen to the background light if there is a black hole. But so ideally, this is what we would like to search for. We would like to scan the sky and look for places where we see these black disks and all this distortion. But the problem is that black holes, although I said that they're big, they're relatively small from this point of view. So we don't have telescopes which can take such sharp images in order to be able to see this kind of a thing. Or almost. I mean, what I just said is not quite true, and I'll come to that at the end of my talk. But keep this in mind. Okay. So then, what is our hope, right, to hunt for black holes? So before I get into that, I want to get over with a few things about the kinds of words I will use and all that. So, for example, the unit of luminosity in astrophysics, things are very, very powerful. They're very bright. They're much, much, much brighter than our table lamps or whatever. So we tend to use a unit of luminosity. If we use watts, which is a normal unit of power, then the numbers become too big. So it gets too clunky to keep talking about watts. So we use a unit which is the luminosity of the sun. Okay, so the luminosity of the sun is about 3.9 into 10 to the power 26 watts. So we use that as a unit of power as 1 L sun. So that thing I've drawn on the screen, L symbol for the sun. So that is 1 L sun. So this is a unit in astrophysics for luminosity. Unit of mass, again, things in the cosmos are very heavy, as you know. The Earth itself is very heavy. So the sun, it turns out, has a mass of almost 2 into 10 to the power 30 kilograms, right? So it's that is the kind of unit we use for mass, and the symbol we use is this big M with a subscript of the sun again. So we talk of solar masses, which is a unit of mass, and so many L sun, which is a unit of luminosity. Now, one more thing I want to talk about is I'll be showing a lot of what are called false color pictures. Now, the reason for this is in astrophysics, especially in the last, I would say 80 years or so, we've looked at not just visible light from the sky. We also look at other frequencies like radio frequencies, X-ray frequencies, ultraviolet, infrared, and so on. Because astrophysical objects emit at all these frequencies. The human eye is only sensitive to visible light. So most of the older astrophysics got done at visible light frequencies. But now, I mean, very soon it was realized that astrophysical objects also emit at other frequencies. And so we have telescopes which observe at those frequencies. But then the eye can't see them, right? So how do we represent those images? Like if I take an infrared image or something. So that is what I'm showing here. So what you're seeing is there is the image of a cat that you would see normally if you had a cat. But if you took an infrared picture of that cat, how to represent it, right? It will look very different from the visible picture. So the one way of representing these is false color images, where you use a color to represent not the color of what you're seeing, but to represent the intensity of what you're seeing. So what you see next to the visible light picture of the cat is an infrared picture of the cat. In fact, both of those, one sort of greenish looking image and a purplish looking image, both of those are infrared pictures of a cat. And as you know, a cat, of course, you know, the eyes of a cat are very warm. We know that the nose of a cat is very cold. Its face and so on are in between. So here, what the computer scientist who has produced this image has done is she has created different colors for different intensity of the infrared light. So white light is lowest intensity in the middle picture, and orange and yellow is highest intensity, and red is somewhere in between, and blue is even less. Similarly, the other picture, which is purplish, they're using black to represent the coldest. So black to represent lowest intensity. So as you can see, a false color picture will not make sense unless you have a key next to it. So that is what is shown here. So you can see this key with the gradation, which shows that white is the highest intensity and purple is lower, and so forth. And similarly for the other picture. So this is what is called a false color picture, where the colors are not real. They are false. They are visible colors, but they are false. And they only represent the intensity of the emission at that particular frequency. So you can have a false color image of a radio picture, an infrared picture, you know, it doesn't matter. These are some more pictures. And here now at the top, at the bottom left, I'm showing you a true color picture of two galaxies in the sky. True color picture means that they have taken light in a red camera, a camera which measures red light, green light, and blue light, and mixed them to give an image which is very similar to what we would have seen with our own eyes. I mean, we can't see such an image with our own eyes because our eyes are not sharp enough. These are images taken by the Hubble telescope, which take very, very sharp images. But the representation is a true color representation. And similarly, so here now, what I'm showing you is images. This is the same image of the planet Uranus. On the left is a so-called true color image. That is, that is the image we would have seen with our eyes if we had looked at Uranus. We can't see such a sharp image with our eyes because Uranus is very far away, etc. With the telescope we can. On the right, it is the same image represented as a false color image. So the brightest part, which is the central part, is represented by orange color. And in this false color image, the faintest part is white. So that is on the upper limb, as you can see. You can see a darkening in the true color image, which is then reflected in the false color image. So just keep in mind that what I mean when I say that I'm showing you a false color image. Okay, one more thing about a very important tool of astrophysicists is spectroscopy. So all of you have done spectroscopy in the lab, and you know that gases show spectral lines, right? And you also know that if you have a gas with a brighter source of light behind it, then you will see a continuum, rainbow-like, and you will see absorption lines, meaning dark lines where that gas is absorbing the light from the background source, and that light is not reaching you, so only the continuum is reaching you. And you probably are familiar with the Fraunhofer lines, which you get if you take a spectrum of the sun. There's a very nice spectrograph that you can build at home using a CD, a piece, in fact, of a CD. I can send a manual of how to make such a spectrograph at home, and you can point it. This is something you can build yourself, and you can point it at the sun. You will see the Fraunhofer lines. You can also point it at any tube light and whatever, and see what the rough spectrum is like. Now the point is, on the top here you can see three strips, three spectra. On the top is something called unshifted. It's labeled unshifted. So this is a spectrum, let's say of the sun or of a star, where you see these lines. Now, because of the pattern of the lines, we can recognize what elements they belong to or they come from. And we know the frequencies at which the atoms of that particular element emit because we've studied them in great detail in the lab. So these are all very well known. These tables are available everywhere and so on. Now, in what happens when a source of light or sound for that matter starts to move, we know that the Doppler effect kicks in. So if the thing is moving towards us, we will see whatever sound or light it is emitting shift to higher frequencies, and that's called blue shift. And if it is moving away from us, then they will shift to lower frequencies, and that is called red shift. Now, in the astrophysics context, if you take spectra of stars and so on, this is what you would see. So the top is the unshifted. So that is what we expect based on what we've seen in the laboratory. That is, let us say that we know that a certain gas cloud or star has some these elements, let's say hydrogen and helium and something else, sodium, oxygen. So we know, depending on the temperature, we know what lines to expect and where, that is what frequency they would come in. So if we see a slightly shifted spectrum, like we are seeing in the middle panel or the bottom panel, then we know that that star or that gas cloud is moving either towards us or away from us. If it's moving towards us, those frequencies will be shifted to higher frequencies. We call that blue shift. And if it is moving away from us, we know that it is red shifted. Therefore, that is to lower frequencies. And we can tell from how much the shift is, we can actually measure the velocity. So this is a very, very powerful technique for astrophysicists. But mind you, it only gives the speed in the line of sight. This doesn't tell us what is the speed across the sky. So to measure the speed across the sky, we have to actually measure position. So we have to measure the position today, then tomorrow, and then day after, and see whether there is a shift in position. Okay. But here I wanted to point out this shifting of the frequencies. So for example, here on top is shown two stars which are shining, and they are in a binary, gravitationally bound. So they're moving around each other, right? Now, if they are moving around like this in the plane of the sky, then we will not see much of a change in their frequencies because there's no line of sight speed. But on the other hand, if they're moving like this with respect to the sky, then they're moving towards us. This one is moving towards us, away from us, towards us, away from us. And this one is moving again towards us, away from us. So if we keep looking at the spectrum of these things, we will see that the spectral lines blue shift, then red shift, and then blue shift and red shift. So we can actually determine the speed. So the Doppler shift gives us the speed of these things, at least in the line of sight. Just 1 second. So now this means that we can measure speeds of things which are suppose there are two stars and they are bound gravitationally, then we can measure their speed. Right? Now, if you remember Keplerian orbits, for example, the orbit of the Earth around the Sun or the orbit of the Moon around the Earth, we know that there is this relationship between the mass, the speed, and the separation. Right? Now, we can use this idea. So the law of gravitation gives us this. This is just simple Newtonian gravity. It gives us this relationship. So we can use this idea to measure the masses of things in the sky. Just 1 second. For some reason, my okay. So now, if one of these, so we do this, we measure this using the using spectroscopy and the Doppler shift. So suppose it happens that there is a black hole gravitationally bound with another star, and we can measure the masses and using the separation. We can measure the separation, we can measure the speed if we look at it for long enough, and we can then see what is the relationship between the mass and the size of the object. Then we can speculate that there is a black hole. So if there's a black hole which satisfies this black hole relationship, we can say that yes, this is a black hole. So using this method, there are about 65 black holes which are known all over our galaxy, the Milky Way. And the estimate, so obviously we only know those which we have measured, and we can only measure those which are like this in binary objects. There may be other black holes which are just floating around, which are not shining, and so forth. These are shining because you have mass which is pulled in by the black hole. So the black hole doesn't shine, but this mass that it is pulling in shines, and so on. So obviously we can only measure the masses of very few objects, but the estimates are that there are about 10 million such black holes. We call them stellar mass black holes, which are scattered throughout the Milky Way. So that is one method. Now, another method is this very exciting new development that has occurred in the last few years. And in 2015, we actually saw the very, very exciting result from this experiment. That is the LIGO experiment, which is an experiment designed to measure gravitational waves. So this is again a consequence of black holes which cannot be predicted by Newtonian physics, and it needs general relativity to explain this. But if you have two black holes so already the black holes are curving space-time. Now, suppose you have two black holes, they're both curving space-time, but let us say they have somehow come in the neighborhood of each other. They will obviously be attracted to each other, and they will, it is predicted that they will get into spiraling around each other, just the way the Earth moves around the sun because of the sun-Earth gravitational force. So they will move around each other, but they will eventually coalesce, because when they're moving around each other like space-time is disturbed very heavily, and as a result you get gravitational waves. And that is what this experiment detected. I won't go into the details because this is something I'm sure you have seen a lot, and there are some very, very good explanations of this on the web. I would particularly recommend the talk by Gabriela Gonzalez when the announcement was made. So this is on YouTube in the NSF. You can find it in the NSF channel. It's also on my Facebook page in case you're interested. So she gives a very, very good explanation of what this whole experiment was about. And so in that way, we can detect black holes. And here, they have detected black holes which are almost 60 times the mass of our sun. So with a mass of 60 solar masses. So that is the at the higher end compared to the masses of black holes which have been measured using the Keplerian orbit technique. So now I want to come back to our Milky Way. So the Milky Way has, of course, many, many stars, as you know, and we see this white patches in the Milky Way because there are lots of, they're not just white, they're not gas or something emitting light. It's because there are, millions of stars all in one, within that area. But you also see these dark lanes in the image of the Milky Way. And the reason for that is that there is a lot of dust also spread in the Milky Way. I say lot, that word lot is ambiguous, because if you take, let's say, a cube of 1 meter, cube size of space in the Milky Way, there's almost nothing there. But if you take the whole Milky Way into account, and add up all the dust that is there, then there's a huge amount of dust. So because of this dust, the dust stops us from seeing what is behind it, because what dust particles do is that they scatter light away in all directions. So because of that, we can't see what is behind. So therefore, even though we are able to see these millions of stars in the Milky Way, we are about 8 kiloparsecs away. That's about 25 light years away from the center of the Milky Way. We can't see what is in the center of the Milky Way using visible light because of all this dust. But infrared light, dust is transparent to infrared light. So infrared light, radio light, etc., we will be able to see from the center of the Milky Way. So a bunch of astrophysicists tried to see what is going on in the very center of the Milky Way, and they were able to do this when they had good infrared cameras. So that is what I'll be showing here. So this is some work which is led by Andrea Yes at the University of California, Los Angeles. So on the top left of the screen, you're seeing a piece of the Milky Way near the center of the Milky Way. And if you zoom in right in the center, there is an area there where there are lots of stars. So I want to carefully explain to you this image, and after that I will show you an animation. But before seeing the animation, you need to understand the image. Now this image, you can see a lot of colored splotches. These are real data. Okay, so they are data taken with an infrared camera, and they represent stars. So this, now imagine you have the whole Milky Way, you have the very center of the Milky Way. This telescope is looking at that very, very center, a very small area. Okay, 1 arc second. 1 arc second is very, not 1 arc second, sorry, it's about 20, which is very small. For comparison, our moon or the sun is 30 degrees. So if you divide the moon into, let's say, 30 strips, each would be a minute of arc. And if you divide that minute of arc into 60 strips, each would be a second of arc. So that is how small this is. Okay, so this is many, many times smaller than the area of the moon on the sky. And they have imaged these stars, and they are labeled, S02, SO16, SO53, etc. These are just some labels given to all of these stars. Now there is a star-like feature in the very center. That's confusing. it's not real data. It's not a star. Okay, it's just star shape has been used to denote that particular point in the sky, and you will understand why when I show you the animation. But that's not real data. So the only real data here are these colored splotches shown as a false colored image, and the splotches are imaged in the infrared. Now, what Andrea Gies and her team did was to take such images starting in 1995 very regularly. So they've taken these images over all these years. They're still taking these images, and then they put all these images together one behind the other to make an animation. So if I take an image, let's say today, and then I take another one next week, and in between, if the stars have moved in the sky, then we will see that in the image, right? If they have moved in our line of sight, we won't see. But if they have moved across the sky, we will be able to see that as a change of position. And then they put all this together to show this animation. And in the animation, again, the only real data are the splotches. So just look at it very carefully. So are you able to see the animation? Can somebody tell me on the voice whether you're able to see the animation? Can somebody,
Yes, ma'am.
can you see
Yes,
the
ma'am.
animation?
Yes, ma'am. You can see that.
Okay.
Yes, ma'am, you can see.
Yeah, so this animation is looping, so you can keep seeing it. So what you can see is that these stars, it's very interesting how these stars are moving, right? They're not moving in straight lines. They're moving in elliptical orbits. You can see that very clearly. And those curves in yellow and pink and so on, they are to guide the eye to show us what path each star took. Okay, so this is itself very interesting. They're moving in elliptical orbits, which means that there is some mass which is making them move in elliptical orbits. Are you saying something? Hello, is everything
No, ma'am.
okay?
I guess there is some disturbance in the background. I guess.
I
Yeah,
request the participants to please mute their microphones. And we will answer if anything is being asked.
Yeah, actually, as a host, whoever is the host can mute all the microphones. So you can just do that for now.
Yes.
Yeah. Yeah, so as I was saying, these stars it's very interesting that the stars are moving in elliptical orbits. But what is even more interesting is that all these elliptical orbits, can you hear me? Okay, all these elliptical orbits have the same focus, and that is what is denoted by that white star. What this means is that it's sort of like our solar system, where all the planets are moving in elliptical orbits around the sun. And we know that the sun's gravity is driving all these planets to move in elliptical orbits. Here, we are not seeing anything there at the focus of these elliptical orbits, but clearly there is a mass there. It is not shining. We are not able to see it, but it is driving all these stars into elliptical orbits. Now, with all these very detailed data, so at the top right of this animation, you can see a counter which tells you the date when that image was taken. So as you can see, the date is running from 1995 into 2018. 2009, yeah, 2018, almost 2019. All of these are driven by this dark object. By looking at the elliptical orbits, using the Keplerian formula of the relationship between the mass and the separation and the speed, we can derive what is the mass that is driving all these in elliptical orbits. Okay, now that mass comes out to be 4 million times the mass of our sun. Secondly, you can see those stars, especially the star which has a orbit which is called SO2, and it has a yellow colored orbit. And then there is this other star which has a sort of pinkish orbit, which has got this really elliptical orbit you can see. These stars, so it's called SO16, so the star called SO16, you can see that they're going very, very close to this point where the mass must be, where this very heavy mass must be. They're going very close and then they are emerging, right? Which means that they are not hitting this mass which is driving these elliptical orbits. That means that this mass has to be smaller than that smallest separation, right? So now you have this mass which we know is 4 million times the mass of our sun, and we know what a small space that it has to be in, because if it's any bigger than that, it will hit these stars and we would see the effect of that. So that gives us a limit on how big this thing is. And so then using the formula that I showed you earlier, we can determine that this must be a black hole. So in the center of our Milky Way, we have a black hole, which is 1 million times the mass of our sun. Okay, so this is a very, very important experiment because it's a direct measurement of the mass of a very, very big black hole. So we call such black holes as supermassive black holes, which means they have a mass which is more than 1 million times the mass of our sun. So what we know is that such supermassive black holes are only occur in the centers of galaxies. So now I will come to another way, in a way, to hunt for black holes. So this is the sky in the region near Spica, in the constellation Virgo. So those of you who are amateur astronomers will be familiar with the star Spica and the constellation Virgo. And you have probably looked at some Messier objects in the sky using your telescopes. So Messier objects are a list of objects which somebody called Messier made a long time ago. And these are objects which don't look like stars, but look like splotches. So they are objects which have, like a fuzzy look to them. And they could be galaxies, they could be nebula in the Milky Way, and so on. So there is this object called Messier 87. It turns out it is a galaxy. This is a very detailed image of that galaxy. In the middle, you see the galaxy. You also see a lot of other galaxies around. You also see these cross-shaped objects. They are stars, and the reason for the cross is the diffraction light that comes from the support of the telescope mirrors. So it's not real, it's an artifact, but very, very sharp objects, bright objects, which are very, very bright, they will show this sort of cross-like feature. And the moment you see that feature, you know that it must be a point object. Mostly stars, but sometimes they could be other things as well. But so the cross, basically the cross is an artifact. It's not of astrophysical origin. But anyway, in the center of this image, you're seeing this galaxy, which is known as Messier 87. It is also known as Virgo A. That's another name for it. And here, I'm showing that same image, but with a false colored image of the radio picture of that galaxy overlaid. So what you're seeing in pink is the false color radio image of this galaxy. And what you can see is that the stars of this galaxy are in the middle, right? You can see that glow in the middle. But from the center of that galaxy, you see these two pink beams come out, and then they're going to a very, very large distance, well outside the galaxy. And there they are forming these two big lobes, right? Now we know that this pink stuff, it is due to what is called synchrotron emission from a plasma. So there are these beams of plasma which are coming out from the center of the galaxy, and they're going out into intergalactic space. Okay. Now, how do we know that the beams of plasma are coming out? You might say, how do you know? There might be stuff which is outside, which is then going into the galaxy. And that is correct. We know, I mean, it could be either. So just by looking at this picture, you can't tell whether it's coming out or going in. But we have images of such objects from very, very close, that is very, very zoomed in. So you see that glow of the galaxy and these two beams coming out. Imagine you image that very central part. We have such images, not for this galaxy. This is a galaxy called Hercules A, for a different one. And there you can see that you can see this stuff coming out. So this, at the bottom, you can see this picture, which is an animation of radio pictures of that very center taken at different months. And you can see that there is stuff actually coming out. You can actually see it, right? So this is how we know that material from the center of the galaxy is coming out. We know it is plasma because it emits this synchrotron emission, which is polarized and so on, and has all the characteristics of synchrotron emission. This is another example from my own work. So here is a galaxy. It's known as the Karaf galaxy, and in the top left, there is a triplet. You can see 3 galaxies together. These are in a gravitationally bound system. And the bottommost is, which is the Karaf galaxy. And we imaged it at a bunch of different frequencies, including visible light and radio light. The black and white image is radio light. And at the bottom right is image in X-ray light. And the radio light is superposed on the X-ray light. And we are detecting these 2 splotches. So it turns out that this particular galaxy was actually 2 different galaxies. And so these 2 different galaxies came together and they became one galaxy. That is why the center of it looks a little distorted. That's why it has this name called the Karaf. And because it looks like a Karaf, you know. And therefore, the 2 galaxies had 2 giant black holes in them. And when these galaxies came together, of course, all the stars got all disturbed and everything, and we can see evidence of that. But in addition, there are these 2 black holes, which are also coming together. So they're not coming close enough that we can see gravitational waves emitted from them using the Earth's facilities. Not that there are no gravitational waves. There will be some, but they'll be very, very weak. But like many millions of years later, these things would come really close and then they would emit gravitational waves. Okay, so now I want to go back to Messier 87 in the Virgo cluster. So on the top left is shown the visible light image of this. It's the same image. Here you can see all the other background stars, but now this image on the top left is focusing on just this galaxy. And you can see there are millions and millions of stars. And on the right is shown the radio picture of this galaxy. So what you can see is, first of all, you can see that from the center, there is this jet of plasma, which is moving towards the top right. Okay, here north is up. So this is moving towards the northwest. And below the optical image, you'll see an image in blue that is imaging the same jet, but in radio frequencies. So this is a false color picture. Then at the bottom is a pink looking image, which is the same thing in visible light, right? You can see this jet-like feature. And then to the right of that, in a purplish color, is the X-ray false color of this, also showing you the jet. But if you zoom out and take the big picture, then what you see is shown in the top right. So you see this jet, and then you can see this other image on top, which shows the jet, but also shows these, you know, big plumes of plasma. And then zooming out still further is what you're seeing on the right. So all that stuff is within that orange patch that you're seeing. And then on a large scale, you're seeing these plumes. So you imagine that there is this stuff coming out from the center. It is creating these jets of plasma. Then it is creating these lobes. And it is creating these huge, big lobes in the sky. Now, there is no way that we can explain all of this except by saying that there is a giant black hole in the center of this galaxy. So all this was known a long time ago. And how can a black, but we don't see the black hole itself. So how can a black hole create all this stuff? So if you have a very giant black hole, I'm missing one of my slides. But you see in this slide, I'll come to the details of this slide later. But at the bottom left, you see, just one second. Okay, I'm somehow missing a slide. So I want to look at this. So in the top right, you see a picture. This is not real data. This is in fact the black hole called Gargantua, which is in the movie Interstellar. So I don't know how many of you have seen the movie Interstellar. It's a very nice movie. I would say all of you should see it. But there's one very interesting thing about that movie for physicists, which is that there is a black hole which features in that movie called Gargantua, and that is shown in the movie. And the simulations that were made to show that are real physics-based simulations. So they are the results of simulations which were made using correct physics. So this guy, a person called Kip Thorne, who eventually got the Nobel Prize for Physics, he was an executive producer of that film, and he was involved in the creation of the simulations. And the interesting thing is, they after the simulations, this company called Double Negative from the UK, who made these simulations, they actually published it as a paper in a scientific journal. So this is something very interesting about Interstellar. So that's why I would recommend, if you're a physics student, or even if you're not a physics student, definitely see the movie Interstellar. The black hole simulations there are created using the best physics that we know today. So this is Gargantua. And what this is showing is how a black hole can create these jets of plasma and these lobes and so on. So what happens is, the black hole, of course, is just sitting there, like in our Milky Way. We cannot see it. Our Milky Way black hole is not visible. We know it is there only because we were able to measure the stars that go very close to it and are in elliptical objects. And then we could calculate what is the mass that is driving them and then conclude that it's a black hole, right? Otherwise, it's just quietly sitting there. Now, suppose you have such a black hole in the center of a galaxy, and suppose you have some stars or gas or something come very close to this black hole. Then what it will do, the black hole's gravitational force is very strong in its close neighborhood, right? So it will pull this material into it, and that material will spiral around it and eventually plunge into the black hole. And so the black hole's mass will increase. Its size will also increase. But the important thing is, the important thing here is that in the process of spiraling around, this material is accelerated very heavily because the gravitational pull of the black hole is very strong, right? And it is accelerated and therefore heated because there is a lot of friction. There's all this gas and stars. If there are stars, they will all be they will all be blown into bits and become gas. They will sublimate into gas, and they will all that material will spiral around, get heated, and eventually plunge into the black hole. But since it is getting heated, before it actually plunges in, it will actually shine because it's so hot. It's like a gas flame or something. I mean, anything very, very hot will shine. So these things will shine. Not only that, they become plasma because they're heated to such high temperatures. They become plasma. And so magnetic fields are created in that area. And these magnetic fields are able to push out some of the plasma into outer space. So you have the black hole, you have stuff going around it, and then you have some plasma which are driven by the magnetic fields away. So all the material, 100% of the material will not plunge into the black hole. because of the magnetic fields generated around them and hot temperatures and so on, some of that material will be squirted out in these jets into outer space. And we know this from simulations, and that is what is being seen here. Okay, so this is how we explain these very, very huge synchrotron emitting plasma jets, which are going out into outer space, well beyond the confines of the galaxy. The only way to explain that is to say that there is a very, very big black hole in the center of this galaxy. And we know many such galaxies. We've known them since the 1960s. We have known many, many galaxies imaged at radio frequencies where they show such emissions. So this is a galaxy called Hercules A. It's one of the most beautiful radio pictures we have. And so it'll appear in lots of different talks. But there are many, many others. Here, for example, which I showed you earlier, this is another galaxy called 3C120, which is shown at the bottom left. And then there was this Karaf galaxy, which also showed, here the jets are not so clearly visible because they are very, very small, and the telescopes we used are not sharp enough to see that structure. But we think that even here, there is a similar structure. And in Messier 87, of course, we have this. And this is another very famous such object. Now, you remember what I told you towards the beginning of the talk, that if there is a black hole somewhere, let's say in the Milky Way, one way to see it would be to actually look for distortions in the light around the black hole. And I also said that that's extremely difficult because we don't have sharp enough telescopes. So this is just imagination. This image that I'm showing you here, the top left is a real image, but the bottom right, the big image where the black hole in the center, that's imagination. And this is how we think it will look, but we haven't really found anything like that. However, if it is a galaxy with a black hole that has these plasma jets, then the light in the very close vicinity of the black hole is shining very brightly, right? I already said that it's accelerated, it's heated up, so it's shining very brightly. So it's not like the ordinary background stars. So the contrast, so here again, I'm showing Gargantua at the bottom left. So this is not real, this is from the movie. The contrast between this hot material and the black hole is much higher than if there were simply some background stars. So that makes it a little easier, to measure. So this was the most exciting, I would say, result that has come in the recent past, the last couple of years. There's something called the Event Horizon Telescope, which was built. This is not a single telescope. It's actually a collection of telescopes spread all across the world. And that is shown in the map at the bottom right. And using these telescopes collectively, we could create a telescope that can image the sky very, very sharply. So for example, if you have a Musumbi-sized thing, which is sitting on the moon, this telescope is sharp enough to image that. Okay, so that's how you have to imagine it. So that is what is meant by what I have written here on this slide, with resolution of 25 micro arc seconds. So micro means 10 to the minus 6. Okay. Now, I already said that the size of the moon is 30 arc minutes, roughly speaking. So the resolution of our eyes is a couple of arc minutes. So that is why we can see all those patches on the moon, which is due to the, the mountains and the craters and so on the moon. We can see those patches with our eye. So that is a couple of arc minutes. So 1/60th of an arc minute is an arc second. And 1/1,000,000th of that is a micro arc second. So this telescope, which is called the Event Horizon Telescope, can see up to, has a sharpness of 25 micro arc seconds compared to a couple of arc minutes of our own eyes. Now with this, it turns out that it is able to image both the area around the black hole in our Milky Way, the giant black hole in our Milky Way, and the giant black hole in Messier 87. And what we expect is what is shown in Gargantua here. So I want to explain that first. So Gargantua, again, is not a real black hole, but it is this picture is the result of a correct computer experiment using the physics we know today as to what will happen around a black hole. So you have this material which is spiraling around the black hole, right? And normally you would see just that. So let me see if I can. Can people mute their mic? So can you mute it for? Okay, so if you just had a dark object and you had stuff spiraling around it, and that stuff is heated and it shines, then you would see something like this. That is, you would see a dark.
Excuse me, ma'am. Excuse me, ma'am.
Yeah.
Participants, we have muted you again and again. You're unmuting yourself back. So please mute yourself. Okay, ma'am, you can carry on.
Yeah, okay. So if you had an object which is just dark, it's not a black hole, right? But it is very massive. Then if stuff came near it, it would spiral into it. It would get accelerated. It would heat up. It would shine. And you would see something like this. That is, you have the shining stuff and you have the dark silhouette, right? But if it is a black hole, if it is a black hole, you will see something that we see in a Gargantua. Just give me a second. So here in Gargantua, what do we see? On the sides, you see this flat structure, which is because of this material that is shining around, right? But when that material goes behind the black hole, normally you wouldn't be able to see it. But because the black hole curves space-time, the light from that stuff behind the black hole is curved over the black hole. I please request you to mute your mics because I can hear disturbance. Can the participants be muted, please? Yeah, thank you. So you have this stuff going around the black hole. Normally, we wouldn't be able to see the stuff which is behind the black hole because the black hole is in front and it would hide it. But because the black hole curves space-time, the light from the stuff at the back will also curve around the black hole and be visible to us. Similarly, some of it will curve around the bottom of the black hole and be visible to us. So that is what you're seeing in the simulation of Gargantua. That you're seeing this hat-shaped thing that is, so you see some of that light directly, and then some of the light that's also direct, but it's coming from the back side of the black hole and curving like this, and also from the bottom of the black hole and curving this way. So you see this very, very typical predicted structure. And that can, so the silhouette of the black hole will look very different from the silhouette of an ordinary black hole. Okay, and this is what the Event Horizon Telescope found. Just 1 second. Just 1 second. Yeah, sorry about that. And that is what the Event Horizon Telescope saw. So they looked at the very, very nucleus of Messier 87, and they found this silhouette of the black hole. So a dark circle in between, and then this ring that you expect, just like in Gargantua. So this is the most direct imaging we have of a black hole. Okay. So here I'm showing you the full image of Messier 87, where these jets have gone out and created these huge lobes. And then if you zoom into that central part, really zoom with a sharpness of 25 micro arc seconds, this is what you see at the bottom right. So that is what we call the silhouette of the black hole. So I'll stop here and I'll wait for questions.
Ma'am, I have a question. What will happen if a black hole reaches its critical mass?
What do you mean by critical mass?
I mean, the maximum amount of mass that a black hole can take in.
Ma'am, your microphone is muted.
Yeah. So as far as we know, there is no maximum mass of a black hole. We don't know that. Black holes have been found with an estimated mass. So the Messier 87 black hole has an estimated mass of 1 billion solar masses. And many such black holes are estimated. Of course, Messier 87 is a direct measurement, as I said. But we have estimates using the power that is coming out of the black hole, and we can estimate what is the black hole mass required to produce that power. And so in the very distant universe, there are many black holes which are known, which are 1 billion solar masses or more. And so we don't actually know that there is a limit.
Ma'am, are there any hypotheses regarding that? I mean, what would happen if the black hole reaches that kind of mass, much more than what's estimated, maybe?
I mean, there's nothing, as far as I know, there's nothing different you would expect.
Okay.
Ma'am, what is the maximum range of attraction of a black hole?
Sorry?
What is the maximum range of attraction of a black hole?
The maximum what?
Maximum range.
Range?
Yes.
Oh, you mean the gravitational?
Yes, gravitational attraction.
The range is infinity, right? But the question is, I mean, the range of any, the gravitational force of, due to you or me or anybody, it's infinity. The question is, at a given point in space, what is the object that is the most dominant? So for example, for us, standing on the Earth's gravitation is the most predominant, right? So it is not the gravitation of myself and my laptop or myself and my house, but it is myself and the Earth. Similarly, for the Earth, the maximum gravitation for the dominant gravitating source is the sun, but the Earth would also be a little bit perturbed by the moon and so on. And so that is the question. At a given point in space, which objects dominate the gravitational force? Because it's a superposition, right? At a given point in space, to determine the gravitational force, you have to add up the gravitational force of everything else. That is everything else in the universe.
Hello, ma'am.
Yeah.
Thank you for
But
your
no, wait, let me finish. So in the case of a black hole, which is in the center of a galaxy, you have all these millions and millions of stars in the galaxy, which create a gravitational field. So there will be a distance from the black hole, some radius from the black hole, from some separation, where the gravitational force due to all these stars will be equal to the gravitational force due to the central giant black hole. So that is what we call the sphere of influence. So inside that sphere, the giant black hole will dominate, whereas outside it will be the gravitational force due to all the stars. So, the black hole in our Milky Way, it's not going to suck up all the stars which are in the entire Milky Way like a vacuum cleaner. It is only going to influence the stars in its close neighbor. Yeah, go on.
Ma'am, is it possible to like black hole to eat an entire galaxy?
No, for the reason I just said. In a galaxy, there are millions and millions of stars, right? So there are typically about 100 billion stars in a typical galaxy. Some are smaller, some are larger, but typically. Now, all these stars, each of these stars has a gravitational field. So at any point in the galaxy, the gravitational field is due to all these stars. So you have to do for a test particle of mass M1, let's say, you have to determine the gravitational force on M1. You have to sum up all the gravitational forces due to all the stars in the galaxy, and ideally also the stars outside the galaxy. But let's, for the moment, ignore those. And then what will happen is, when you add up all of that, the giant black hole's gravitational force will turn out to be very small, and the most of the gravity will be due to all these stars. So typically what happens is, if you have, say, a spiral galaxy, all the stars are moving very slowly, sort of in a, roughly speaking, spiral structure. If it is what is called an elliptical galaxy, then all of them are moving in sort of elliptical orbits. They're swarming. Now, they're all swarming under the around the center of the total gravitational potential well, not because of the black hole. So the black hole cannot gravitationally influence all the stars in the outer reaches of the galaxy. So they will only influence. So therefore, unless there is another galaxy which comes by and gravitationally distorts these star orbits, which drives some of them to the center of the gravitational potential well, which happens sometimes. Unless that sort of thing happens, the swarming stars will just stay there, and the central giant black hole cannot, attract or influence or perturb the orbits of all those stars. Yeah.
Ma'am. Hello, ma'am.
Yes.
Ma'am, under what circumstances does the Hawking radiation from a black hole start to function? Is there any specific criteria, or it happens all the time?
Yeah, so I'm not an expert on this, but the Hawking radiation, first of all, it's a theoretical concept and it has never been observed. Okay, so the Hawking radiation is something that goes contrary to this idea that nothing can come out of a black hole. So it is a quantum mechanical effect which results in some energy loss from the black hole. Now, it turns out that the Hawking radiation, the amount of Hawking radiation, is inversely proportional to the mass of the black hole. So very tiny black holes, these speculative micro black holes or electron-sized black holes or something that I mentioned, these are not seen. They've never been detected in the laboratory, but they're speculative. But if there were such a black hole, then the Hawking radiation would be very large. As a result, these black holes would just evaporate very quickly. But the amount of Hawking radiation is inversely proportional to the mass. So if you do the calculation, it turns out that the Hawking radiation that would come from even a stellar mass black hole, and definitely from these giant supermassive black holes, is extremely small, extremely small. So the amount of time it would take for a giant black hole to kind of significantly lose its mass through Hawking radiation is it's beyond the age of the universe. So that is what we understand.
Hello, ma'am. Hello, ma'am. Hello.
Yes.
Can you put some light on the gravitational waves?
No, but specifically, what do you want to know? I mean, gravitational waves are created when the space-time is disturbed, and the space-time is disturbed when things move in the space-time.
Ma'am.
Yes.
the formation of black hole follow the conservation law of energy? As we know that the mass of sun is very, very low in the comparison of black hole.
Yes. Yes, so conservation of energy is there, yes. For example, when you have all these black hole mergers which have been detected by LIGO, the very first one which was discovered, that was two very massive black holes, so something like a 60 solar mass black hole merged with a 25 solar mass black hole, and then you got a coalesced black hole which was double the size of these two, but it was not exactly double. About 3 solar masses of mass was converted into energy. So yes.
Ma'am, does black hole have a lifetime or they remain forever?
So they have a lifetime. So this idea of Hawking radiation, which as I said is a theoretical concept and has not been observed, but if it turns out to be there, if it really happens, then that would give black holes a lifetime, because the black holes would lose their mass through Hawking radiation and eventually evaporate. But as I said earlier, since the amount of Hawking radiation is inversely proportional to the mass, very, very small black holes will emit a lot of Hawking radiation and so have a very short life. Whereas very massive black holes would take a long time for all of its mass to evaporate with Hawking radiation, and that length of time is calculated to be larger than the life of the universe. So yeah, in that sense, they're not quite.
Ma'am. Hello, ma'am.
Yeah.
Hello, ma'am. Hello, ma'am.
Ma'am, I want to ask you that in the time of image processing of the black hole, scientists have chosen the M87 galaxy, but why they choose the M87 galaxy? They can choose M31 galaxy also. It is more nearer to our galaxy. So
yeah, that's a very good question. So there are many factors that go into this. So they have to decide what are the chances of detecting the silhouette, because what we want is the silhouette, right? Now there are many things here. First of all, the sharpness of the telescope has to be such that it has to be smaller than the size of what you're trying to detect. So that 25 micro arc seconds that I said, that is the sharpness of the Event Horizon Telescope. That is the sharpest image ever made. And so the silhouette that you're trying to detect has to be bigger than that slightly in order to be able to detect that. So that is one question. Now, what will determine the size of the silhouette? It is the mass of the black hole that will determine the size of the silhouette. So bigger the mass of the black hole, the bigger the silhouette. At the same time, that object has to be close to us also. So closer the object is to us, the galaxy in this case, the black hole is to us, the larger it will appear in the sky. So there are these two factors. Then there is the question of being able to see anything at all. So if you have a black hole that is just quietly sitting there without material spiraling around it and plunging into it, there isn't all this material which is heated and shining and so on. So then, that contrast that we want between the material that is surrounding it and the black hole itself, that we want that contrast to be high. Only then we will be able to actually image it. Now it turns out that Messier 87 and our Milky Way black hole are the only two where we have a hope, of detecting the silhouette. Milky Way, because it is very close by. It is a 1 million solar mass black hole. It doesn't have a huge amount of material spiraling in, but it does have some, and they are yet to actually publish the silhouette of the Milky Way black hole. They haven't been able to do it because it's a very complex data analysis process, because the contrast is not very high. I mean, at least that is one of the reasons. And so the Milky Way black hole and the Messier 87 black hole were the best candidates. Messier 31, Andromeda, it has a black hole. It has a giant black hole in its center. We know that from other measurements, but it's very hard to measure the silhouette because the you don't have material. It is not an accreting black hole, so it is not an active galactic nucleus, so you don't have material spiraling around it and plunging into it, so you don't have that high contrast. I'm sure they have observed Messier 31. You know, the Event Horizon Telescope is only slowly publishing all its results, so they probably observed it, but it would not be an easy object to get data from, because you don't have this high contrast.
Ma'am, can two or more black holes can merge together?
Hello.
Yes, that's already been seen. I mentioned LIGO, the experiment LIGO, where they actually measured merging black holes.
Oh, yes.
Ma'am,
Hello, ma'am. As you say, Event Horizon Telescope is a global network of radio telescopes.
Yes.
So I believe there's a lot of data. So how, like, this data is stored? Like, can it, like, how do we use that data? Like, can we transfer it through a computer, or we need to transfer it physically?
So they gather these data at the different telescopes, and then they bring them all to one place. The data are of course stored on, you know, digitally. Then they bring them all to one place and do the so-called interferometry. It's called. So it's like the double slit experiment that we would do, except that these two double slits, the equivalent of the two double slits, are two telescopes which are at very different places. So then they have to bring all that data together and then do that interference in the lab, and then produce these images. So it's a very, very, very complex process. Firstly, complex.
What is the size of the data?
Sorry?
What is the usual size of the data?
Oh, I don't know off the top of my head, but it's very, very, very huge.
Excuse me, ma'am. Excuse me, ma'am. Excuse me, ma'am. May I just barge in? Ma'am, actually, the speaker who just now asked a question, I think she's Mridusmita Buraghai from Tokyo. Is it Mridusmita?
Yes.
She is doing her postdoc from Tokyo University, and she was the person who has made it possible to call you here. Actually, she gave me your contact, so I welcome her. She's speaking from Tokyo. She was her alumnus, ma'am, and she doesn't want. Yeah, ma'am.
Actually, my background is not so good now, so I didn't want to come in video, but maybe
she doesn't want to come. Okay, ma'am. Thank you, ma'am. Thank you, ma'am.
Yeah. So, Mridusmita, you should go to the Event Horizon Telescope website.
Yes,
I mean,
ma'am.
all these things are, very much there.
Yeah.
And eventually, I'm hoping that they will make their data public so that anyone can take their data and play with them.
Yeah.
But it's a complex process. So it involves, actually these telescopes like this, they don't directly take a picture, because at radio frequencies, if you directly take a picture, you don't get a very, you can do that only with single telescopes, and single radio telescopes don't give you sharp images. The advantage of radio telescopes is when you put them all together and make this array of telescopes. That's when you get this very, very sharp images.
Yeah.
But in order to do that, it's complicated because what this array is measuring, it's not taking a direct image, it is measuring the Fourier transform of the sky. It is not measuring the sky directly. So you have to take the data and do the inverse Fourier transform, which is a very computationally very heavy process.
Yeah.
And then there's a lot of other complications involved because there's a lot of gaps in the data and all that. You have to interpolate and all that, and so it's pretty complex.
Yeah, I work with infrared telescopes, so I think this kind of complexity we don't face easily.
Yes.
Yeah, so that is why I was wondering.
Yeah, but the Very Large Telescope has infrared cameras where they do interferometry.
Okay.
So there it is complicated.
Okay, thank you.
Yeah.
Excuse me, ma'am.
Hello, ma'am.
Ma'am, may I just interrupt a little bit? I thought there was a question about the size of the data collected by the Event Horizon Telescope. Ma'am, fortunately, I happen to know the size because I was presenting a seminar on this very topic. It was the size, the the size of the data that was used to publish the data on the Messier 87 black hole image was 5 petabytes.
Yeah, thank you very much. That's nice.
Okay,
That's
thank you,
nice.
ma'am.
Thanks for sharing that.
Hello, ma'am.
Yes.
Ma'am, what happens to time inside the event horizon?
Yeah, so that is outside my area of expertise. I don't work with what happens inside the black hole. There are other people who do. So there is this website in the University of Colorado Boulder where I forget the name, but I could send it to you. I can send you the website perhaps, or you can even search for it in University of Colorado Physics Department website, where this scientist has done a lot of simulations of what might happen inside a black hole and shown the results and so on. It's very nice. So you should go there.
Okay. Thank you, ma'am. Ma'am, what happens to time actually near the black hole?
The time gets distorted because space-time is distorted.
Time.
Yeah, so the idea is that the person who is actually entering the black hole, this is what is happening in Interstellar also with the Gargantua black hole. So the person who's actually entering the black hole will not, so you cannot, a human being won't be able to enter a stellar mass black hole, because then the tidal forces at the surface of the black hole will be very heavy. So objects will not survive there. However, when you get these giant black holes, supermassive black holes, which is what Gargantua is, then the tidal forces at the surface of the black hole are not that strong. So it is possible to think about or imagine, entering the black hole and so on. So, I mean, this is all speculative. It's not like something has been seen doing this. But at the speculative level, what is assumed is for an observer outside, they will, just a minute, they will see sort of it going on, into infinity. So they won't actually see the person enter the black hole because the time will stretch a lot.
Thank you, ma'am.
Hello, ma'am.
Yeah.
Yeah, ma'am. Actually, photons are massless particles, right? So if forces are to gravitational forces are to attract on them, then means both the masses should be F equals to means m1 m2 by r square. But if one of the mass is 0, then net force should be 0, right? But the light remains inside the means outer part of the black hole in the event horizon. If mass is 0, it should just come out of the black hole, right? But forces do attract the light.
Yeah, so I think, I mean, I'm not the expert on this, but I think it's not correct to think in terms of force acting, because see, light travels along the geodesic, and the geodesic of the space-time gets distorted, and that is why the light curves. It is not because the photons are being accelerated. It's because the space-time is curved.
Okay, ma'am. Thank you, ma'am.
Hello, ma'am. Excuse me, ma'am.
Yeah.
Actually, we have received a question in the chat box. So the question is like, is there any theory that explains the stability of a black hole? I mean, what exactly balances the inner gravitational pull after the collapse of Newton's star, or every black hole gets into the same size singularity?
I'm trying to see. It's a long question. Let's see. What exactly balances the inner gravitational pull after the collapse of a neutron star? Oh, you mean what is the equivalent of the force in a neutron star that holds it up? I actually don't know. I mean, this business of singularity is something that is debated. It is not something one can measure. What we do know from measurements is that whatever general relativity predicts, in terms of the size of the event horizon compared to the mass has turned out to be correct in the case of the Massey 87 black hole silhouette that the Event Horizon Telescope discovered. So Massey 87, as I showed you, it's producing all these radio jets and all that. And there have been, and there are these, there are no stars very close to the giant black hole that we can measure, but there are gas clouds which emit spectral lines, which are moving very close to the central black hole. And by measuring those gas clouds and their Doppler shift and of the spectral lines from those gas clouds and so on, there is an estimate of what is the mass of the black hole. And therefore, there is an estimate as to what is the size of the event horizon and how big that silhouette should be on that. And what the Event Horizon Telescope has measured is consistent with that. But as far as the singularity is concerned, the singularity is what is theoretically expected, but that is not something that we've measured. So yeah, I don't, I mean, the short answer to your question is I don't know.
Hello, ma'am.
Yeah.
Ma'am, I wanted to ask that if the black hole is really a hole or is it a solid?
Well, we know that mass plunges into it and it grows. I mean, all evidence is supporting that idea. So we haven't actually measured the mass changing. Okay, so it's not like we've determined the mass of a black hole and then after 1 year we've determined it again and stuff has plunged into it so we can measure a change in the mass. That has not happened. But as per current predictions, and there is nothing contradicting that, the mass of the black hole is growing. Does that answer your question?
No, ma'am. I was actually asking that if the black hole distorts space and time, it must be of some mass. But how can a hole have a mass? I was asking that.
I guess it's called a hole because anything that would come. What else would you like to call it? Would you like to call it black ball? I mean, black hole is just a name, right?
I don't know.
So it's meant to convey that anything that falls, anything that comes close to it, will plunge into it. That's what it's, I think, meant to convey. But you should. I mean, you should understand it's a name. It's a name to describe this phenomenon that we know, where there is this relationship between the size and the mass, and if that relationship is satisfied, then even light cannot escape from it. That is what we know. So instead of saying all those 2-3 sentences, we say black hole. Okay, so that's all it means. So you shouldn't take it too literally. Yeah.
Do black holes have a magnetic field?
Yes. So as in the black holes themselves don't have a magnetic field. The only properties that are permitted are mass, size, and charge, electrostatic charge. But if you have mass which is spiraling around and becoming plasma, and that creates magnetic fields, those magnetic fields you would expect to sort of loop, sort of the way we imagine it is at least like looping into the black hole. But I don't know if it is correct to say that there are magnetic fields inside the black hole. I'm not sure. But definitely magnetic fields are created in the very, very close vicinity of the black hole, because of which some of that plasma is coming out.
Ma'am, you just said that the mass increase or decrease of the black hole is not measured till now, but when we say that it is about 30 times the solar mass or billion times the solar mass, do it actually interpret that the mass of the star before the black hole was formed, or is it actually the present mass of the black hole?
No, that is a present mass. So yeah, that's a present mass.
While the mass is being sucked inside it, so the mass inside it should increase, and the mass should be gradually growing faster. So when we say that it is 30 times the solar mass, it means that at the present moment it is that, but beyond, as it grows in time, the mass may increase, but we have not measured it.
Correct. So the mass would increase. I mean, we expect that the masses of all these things are increasing, but they are not increasing on a time scale with which we can measure. And of course, one small modification to what you're saying is when we say something is now, it's actually sometime in the past, right? Because light has taken that much time to reach us. So that's one thing in astrophysics that you have to remember. For example, light takes 1.3 seconds to reach us from the moon. So if we see something on the moon now, it actually happened 1.3 seconds earlier. Similarly, if we see something on the sun, that happened 8 minutes earlier. And so things in distant galaxies happen many, many years earlier. By the time the right light reaches us, it takes time. So that's one modification to what you're saying. But what you're saying is correct, that apart from this delay because of the light travel time, the current mass is what we are saying it is. So for example, Messier 87 currently has a mass of 1 billion solar masses, and it is increasing. As far as we know, it is increasing, although we have not actually measured that increase.
Hello, ma'am.
Yeah.
Ma'am, that means for the mass to increase significantly, we must have to wait for about 100 or 200 more years. Then we can say that it has slightly increased. But on a very small scale of time, we can say how much mass has increased.
Yeah, it's also the precision with which we can measure the masses, right? So the older, when I said that Messier 87 was known to have 1 billion solar mass, giant black hole in its center and all that, those methods are not that precise. So we won't be able to measure increases also. Event Horizon Telescope measurement is more precise. It's a very good question, actually. I haven't thought about how long it would take if we kept measuring the mass with the Event Horizon Telescope. I've not thought about that. That's something that I need to think about. When it comes to the stellar mass black holes, which we measure the masses due to Keplerian orbits, even there, the time scale, the precision and the time scale, it's related to both, right? The precision and the time scale are not enough for us to be able to actually measure. But I don't know the exact time scale. I haven't thought about that. That's a very good question, and I need to think about that.
Thank you, ma'am.
Hello, ma'am.
Yeah.
Ma'am, how can we locate an exact position of a black hole?
Sorry?
Ma'am, how can we locate an exact position of a black hole?
So we can't locate if it is just a quiet black hole sitting there, because we can't even see it, right? We can locate the position if there is some shining material around it. So we just so in the case of the Milky Way black hole, I showed you how the position is determined, right? It is the center of, it's the focus of the elliptical orbits of the stars which were measured around the Milky Way. And in the case of the Messier 87 black hole, it is so in the Messier 87 black hole, it is here, which is at the center of all of this. So inside that square box. And in the case of the Milky Way black hole, it is, So it is that position of the star because that is where all the elliptical orbits have the focus.
Okay, thank you, ma'am.
Ma'am, I have a question.
Yeah.
Ma'am, let us consider a star now which died have a satisfying mass which can turn into a black hole. Does the space around it curves more when it turns into a black hole?
Yes, because when it is a star, it's much bigger, right? So then you cannot approach, if you are on the surface of the star, you can't approach closer than the surface.
Yes, ma'am.
But when it collapses, then you can start approaching it to a much closer extent because it's much smaller.
Ma'am, I'm asking.
And in that place, it would be much more curved. The space-time would be much more curved.
Oh, okay. Thank you, ma'am.
Hello, ma'am. Ma'am, are there any unusual quantum phenomena that are expected near the event horizon of a black hole? Because the particles are accelerated to extreme speeds. So are there any unusual quantum effects that you all expect?
Okay, so quantum effects is outside my area of expertise. So the short answer is I don't know. Hawking radiation is one quantum effect near the event horizon of the black hole. Yeah, more than that, I can't say. I mean, what we know and what what we can measure is the relativistic magnetohydrodynamic effects which happen in the vicinity of a black hole. They're creating these very powerful magnetic fields which drive some of the plasma away from the black hole instead of that plasma falling into the black hole. But quantum effects, the only quantum effect I know of is the Hawking radiation.
Okay, thank you, ma'am. Ma'am, could
But
you
of
also
course,
share
from near giant black holes, it's nearly impossible to measure.
Hello, ma'am.
Yeah.
Ma'am, could you also shed some light on Einstein-Rosen bridge on that hypothesis?
Sorry, which one?
Einstein-Rosen bridge, black holes and wormholes, something like that.
No, I don't know anything about that.
Okay, ma'am. Thank you, ma'am.
Ma'am, is it possible for us to make a micro black hole maybe? Is it possible for us humans?
It's not been done so far. I don't know how you would do it.
Yes, somebody told me that it's possible with the particle accelerators, but I don't know it's true or not. So I asked you.
No, so far there's been no evidence so far. They've tried to detect signatures, but yeah,
Okay,
no success has been reported.
Okay.
Hello,
ma'am.
Yeah. Actually, there is a question in the chat window that even light can't escape the gravitational field of black hole. How Hawking radiation escape that field?
Yeah, that's a good question, but I don't know the answer to it.
Okay, ma'am, I have one question. Ma'am, you have shown a slide where around the black hole, I mean the matter, it starts spilling out from the sides of the from the sides of the black hole. From the center, the matter starts spilling out, just like in the form of a plasma. So my question is, I mean, if so much of matter, yeah, ma'am, this slide.
You
yes.
mean this one? Okay.
Yeah, this one. Yeah. So I mean, if there is this matter has been spilling out since long time. I mean, so how much matter is exactly there, or I mean, after how long can it start spilling it, and where does this additional matter go after it is being out of that particular region?
So this is plasma. So in the beginning, it has a lot of kinetic power. So the plasmas are, squirted out into intergalactic space, but eventually they'll, run out of kinetic power, and these plasma lobes will hang around in intergalactic space for a long time, and they will diffuse like you would expect any blob of plasma to diffuse. And yeah, and then eventually, eventually they will just diffuse to such an extent that we won't be able to detect them. But
thank you, ma'am.
That's what will happen.
Thank you, ma'am.
Hello, ma'am.
Yes.
Ma'am, we have seen in general theory of relativity that mass bends space and time. How does mass bend space and time then?
How, I won't be able to tell you. I mean, the only way to it is to look at the equations of general relativity and see what they predict.
Excuse me.
By mathematics, but
I mean, it's
how it interacts with.
It's not just mathematics, right? I mean, there is the mathematics, but the mathematics has certain predictions, and those predictions have been borne out, right? I mean, you know the famous experiment by Eddington, where he first demonstrated the bending of light during the solar eclipse of 1915, and subsequently there have been many experiments which have confirm this. So gravitational lensing, it's called. The masses behave like a lens, and they bend light, and the effects are seen. And we have many examples in the sky of this. So in that sense, it is well established. If you ask the question how, I won't be able to answer. I mean, how does how is the answer to that is from the equations. Like if you mean by how, if you mean how much curvature with what mass and all that, that the equations tell us.
So, ma'am, should we stop the question answer session now?
Yeah, I mean, if there are a few more questions, I can take them.
Actually, ma'am, there are 2 questions in the chat window.
Okay.
So, shall I read out?
Yes, please.
The black holes, which are not in the binary systems, how do we measure its masses? I think there's a kind of mistake here. Is observing their spectra enough for that?
No. So the thing is that the reason we are able to study black holes which are in binary systems, I didn't really get into the details of it, but let me just show that artist's impression. Okay, maybe I can show you this one. So you have wait. So do you see that image in the top right corner? Where there is stuff spiraling around and there is a jet. Can you see that?
Yes, ma'am.
Okay, so what is shown here, it's not real data, but it's an artist's concept. So when a black hole and another star are bound in a binary system, what can happen is that when one of the stars is evolving, it can expand and become larger. And when that happens, some of its mass comes into the influence of the black hole and leaves the star and starts getting sucked up by the black hole, which is what you're seeing here. Now, when that happens, obviously we'll be able to see the black hole because of this stuff flowing into it. It creates this what we call accretion disk, which is very hot and it shines and all that, just like in the giant black hole case. So we are able to see this black hole in X-rays. So the way it works is the system around the black hole is visible in X-rays because stuff has come into it from the other star, from its binary companion. And we are able to see the other star because that's a regular star which will show spectra and so on. So that is how we are able to study these systems. Now, if the black hole were not in a binary system and just floating around, then it's just a dark object and there is nothing around it which is, nothing can come near it, nothing around it to spiral in and go into it. So then we won't be able to see it. So the only way to detect such black holes is by lensing. That is, if suppose by chance you have a star which is shining and you have another black hole which passes in front of it as we are watching this star. So let us say we are constantly watching a star and taking some measurements, and another black hole and a sort of random black hole just sort of passes in front of it. When the black hole is passing in front of the star, this light from the star will get distorted. And so the light from the star will change. We will not see any shape or anything because we don't have such sharp observations, but we will see that the light of the star was steady for some time. Then when the black hole passed it, it increases and then decreases again. Now, such experiments have been done, and it's very, very difficult to do because we don't know when a black hole will pass in front of another star, right? So the only way to do it is to survey a large piece of the sky and constantly monitor stars and so on, and then see how this light changes. And the light can change for a variety of reasons. So we have to determine whether it is indeed changing because there is this black hole which passes in front of it and all that. So that's a difficult process. But now we have telescopes which are already in operation and which will be in operation also, better ones in the future, which are just constantly monitoring pieces of sky on a regular basis. So these stars, their brightness is measured, and so we will know if their brightness changes, and then we can figure out why that brightness has changed. And we expect that at least some of those changes are because a black hole is passed in front of the star. So this is called microlensing. This effect, and so that is a way to find such black holes. But then the black hole will pass in front of it and go away, so we won't be able to like study that black hole constantly. We will just know that a black hole has passed in front of a star and has affected the light from the star. We won't be able to study that black hole because there's no way to know where it went and so on.
Hello, ma'am.
Ma'am, Ma'am, a last question given in the chat box. There are so many coming, but I'll just stop with this one. It's quite short and curt. Are black holes vacuums?
I don't know. No, they can't be vacuum, right? I don't know. They can't be vacuum because all this stuff is plunging into them, and that's how they have a mass. So I don't know. I don't know what that question means actually. You need to ask a general relativist that question. And earlier, in one of the early questions, I had pointed out to a website on the University of Colorado webpage where they have looked at what might happen inside a black hole and so on. So the interesting thing is the density. We have this concept of density, right? And we determine the density by dividing the mass of an object by its volume. That way we get its average density. Now, I don't know whether the concept of a density inside a black hole makes sense or not. Okay, I don't know that. But I mean, some people may know it. I don't know it. But if you do play with the numbers, and if you take the mass of some black hole which is known and divide it by its volume, you will get some number, which is the density. and this number will reduce as the mass of the black hole increases. So the larger the black hole, lower this number of ratio of mass to volume. You can determine that by just looking at the formula for the mass and the relationship between the mass and radius of a black hole. So giant black holes actually have very low density. So, there is this joke that people say, what's it like inside a black hole? Just look out of the window, because the density that whatever, I don't know whether that has any meaning, but if it has any meaning, that number comes out to be same as the density of our atmosphere. I don't know if that answers your question, but at least I've raised some more questions for you, and you should talk to a general relativist.
Ma'am.
Yeah.
Yeah, I
have a question.
Yeah, okay, go ahead.
Ma'am, do black holes emit radiation? Because if they do, we can directly measure the radiation from Earth and detect whether if there is a black hole or not in a certain position in space.
Yeah, I think I've already answered that question. Black holes do not emit radiation. There is this theoretical expectation that they will emit Hawking radiation, but it is very difficult to measure, because the larger the black hole size, the lower the Hawking radiation, and it has not been measured for any of these black holes, either the stellar mass black holes or the supermassive black holes.
Okay, ma'am.
Thank you, ma'am. I think we should stop here. Okay, ma'am. And I think thank you would be a too small a word to express the. Actually, you have taken us from the photograph of a galaxy down to the bleep into the black hole. In fact, you have stimulated quite a lot of the young minds, quite a lot, because I can even see questions and also answers in the chat window. So it was really a wonderful experience, and we thank you for all this, and thank you would be too small a word, as I have already said, and we hope to have you some other day when you are free, ma'am.
Yeah, sure, it'll be a pleasure. Yeah,
Yes,
I really enjoyed all the questions.
Yes, ma'am.
And yeah, it was, and thanks Mridusmita for coming on as well. I hope to meet you sometime, and I hope your work is going well.
Yes, Maya. Yeah, I hope to look. I hope to meet you soon someday.
Yeah.
Okay, may I now request Dr. Kanchan Kaur, my colleague, to just give a formal vote of thanks. But before that, I would like to make an announcement for tomorrow's talk. Tomorrow's talk is by Arnab Bhattacharjee. He is from the Tata Institute of Fundamental Research. And I want to point out that it's going to begin 1 hour in advance to today's talk. That means our talk tomorrow is scheduled at 10:30 in the morning. So please be here by 10 a.m. So thank you. Over to Kanchan, Dr. Kanchan Kaur. Dr. Kanchan, are you here? Dr. Kanchan?
Am I audible?
Yes, you are.
Hello?
Yes, you are audible. Yes.
Thank you very much, Rasmi ma'am. Thus, we have come to an end of first lecture of our 5 days lecture series in physics, and it is now time to propose the formal vote of thanks. First of all, for Physics Department of the Digboi College, I would like to offer our sincere thanks to today's resource person, Professor, for spending her valuable time with us and delivering an interesting talk on hunt for black holes. It was quite informative, and we are really enlightened with your knowledge and presence in this virtual platform. Thank you very much, madam, for your talk. We are really grateful to you, madam. I also thank our principal for participating in this webinar. Thanks to Dr. Joyanta Handikoi sir, coordinator of IQAC, for his constant association with us and providing us that technical help. And at last but not the least, I offer our sincere thanks to all the students, faculty members, and research scholars across the country and globe who actively participated in this webinar and making this webinar a grand success. With these words, I am concluding my speech, and now over to Rasmi Madam for her concluding remark. Thank you.
Thank you, Kanchan. With this, we come to an end of today's session. We have 4 more interesting sessions waiting for our participants and ourselves too. So have a good day. Thank you very much. Thank you, ma'am, Prajval.